In this video, we will learn how to set values for distribution coefficients for trace elements to be used during calculations in Petrolog. To enter the values which you would like to use for distribution coefficients, click on Tools in the upper menu and then choose the Set D-Values form. When you first come to this form, you can see that values for all distribution coefficients are set to 0, which means that they would be considered completely incompatible in every phase, and their concentrations in every phase will be 0. On this form, the elements are listed on the left, and you can see that there is a large number of elements which you can include in your calculations in Petrolog, and the other columns are for entering values for a specific mineral. For example, if you would like to enter a distribution coefficient for samarium and clinopyroxene, if we scroll down, we'll see samarium is in this row here, clinopyroxene is in this column, and if we enter here value of, for example, 0.4, that means that during calculations, if your analysis contains samarium and clinopyroxene is crystallizing from the melt, then that will be the distribution coefficient to determine the concentration of samarium and clinopyroxene. You can enter the values which you believe are appropriate for distribution coefficients for your calculations for any element in every phase. Petrolog also offers for some elements models that predict the D-values for different elements. Unfortunately, there aren't that many models available, but those which are currently in the Petrolog are, for example, Blandian wood for strontium in plagioclase. So if we click on strontium for plagioclase cell, you'll see a form pops out, and it pops out because there is a model available for that element, strontium, in that mineral plagioclase. And what you can see is that there is more than one element is actually available in this model. There's also barium. So if you want to use the model for both, you click Set for all elements and then click on the model, and what you can see is that you will have Blandian wood 9091 model assigned to both barium and strontium. So note, there isn't a value. The value will be predicted by the model. There is also a model for, let's say, nickel and olivine. So if we click in here, you can see that BT91 model involves cobalt and nickel and olivine, but let's say you are not interested in cobalt from this model, only nickel. So if you untick Set for all elements and click now on BT, you can see that nickel will be calculated using the model of BT91. If you close the panel, what you can see, we entered a constant value of 0.4 for samarium for clinopyroxene, and we will use calculated values for these for this element and these phases. If you then change your mind and you don't want to use, let's say, the model of Blandian wood for barium, only for strontium, you can override this with the value you prefer to use. So for example, if we click here and instead of choosing the model, we say we know what the value is, and the value is 0.3 and we believe it is constant, you can see that we can now have that constant value instead of the model. So strontium will be calculated using the model and barium will be calculated using the constant value. Now, once we've done this for all the elements and minerals we are interested in, we can save this set so that we can use it later on if needed. To save the set, click on this button, Save the set of these, and let's say we want to call it my D set, and we click Save, and what you can see, that file now appeared in the same directory where we have Petrolog, and it will be available for use in the future. So to demonstrate how this can be done, let's say we want to now erase everything. So if we set all these to 0 and click OK, and now if we go into the same form, you can see there are no values selected, but we load a set of D from that file we've just created, and you can see they're now back. And if we click OK, we can now calculate with this set of parameters. In the next video on distribution coefficients, I'll describe a slightly more involved case of distribution coefficients being defined by the selected mineral melt model.